put it on your desktop and unzip it. Okay, so I have a number of things in my desktop. So this can be, and you simply have, okay, time bundle to. Oh, where is crime bundle? I'm not able to see it. Okay, I already have it. Okay, so unzip it and take your KNIME bundle here on the desktop. Keep it on the desktop. Then you have your space and preferences. Okay. Install update. Then go in available software sites. And you have to click here, add. You selected the first one and import. Local. And you have to repeat these, for example, that I want. I put in my desktop, so desktop, KNIME bundle, and select it. So pay attention here. You should have the name all together. So it's very important not to have some spaces. So not Daniela space Rotelli, but Daniela Rotelli all together. Then this is the path to the bundle. Okay, so Daniela Rotelli, desktop, because I put my bundle in the desktop, and this is the name of the bundle. Once I've done it, I simply say, I put a name, KNIME bundle finder, okay, add, and this must be flag. Apply and close, okay. Then menu, here, install extensions, and here you have to click on to select Python. Sorry, not Python, but Finder. Okay, Finder. And you should see Finder here. Okay, so now we start. You have to go in the Moodle, not this one. You have to go in the Moodle. Okay. Then from here in the Finder site, in the data analysis, login. In the data analysis part, okay, here you find data and workflows, okay, and you simply have to click to download everything, okay. Once downloaded, you will find this folder, data analysis non-programmers. In this folder, you will see the list of data set and the workflows. And once you see the workflows, so put everything in your desktop so it's easier to find it. Once you have your workflow, you simply have to go in your local space here and then import workflow one by one. So here we have data analysis non-programmers, workflows, and workflow 0, open. I don't do it because I've already installed it. And then you will see the list of installed workflows here. So you need to do it one by one, okay? The folder is here in dataset and workflows.
Okay, so good afternoon, everyone. I'm Riccardo Guidotti. I'm assistant professor at University of Pisa, and this afternoon and tomorrow morning, I will guide you towards this part about practical data analysis we prepared. And together with me, there will be Daniela to help with technical issues, and there will be also some tutors. They should be already connected. We have Andrea Iomi, Andrea Fedele, Marta Marchioni Manerba, and Martina Cinquini. Because later on during the lecture we will split up into breakout rooms and I will guide one of them and the other tutors will guide the others to do exercises and do directly things together, hoping that by that time everyone can manage to execute the workflows such that you can experiment. So a very, very short introduction. So we are doing lecture in parallel in 4 groups. We are the non-programmers online, and we will use NIME as tool to follow the. Oops, sorry. I call it NIME, and it appeared. The magic. Tomorrow morning, instead, we will have a session in which we will be split into 4, like now, and then there will be plenary sessions altogether. Okay, something important we need to mention. All the dataset you just downloaded following Daniela's instruction are fictitious and synthetic datasets. So regarding curriculums and job offers. There are about 200 job offers and between 25 and 150 curriculums, but each one of them have been completely synthetically generated. So these data are not representative of any situation, of any real context. You cannot use them to derive any kind of analysis. They are just meant to help you understand the real processes and how they can be done. So they resemble real data, but they are not even inspired by real data. I mean, they are plausible, meaning 80% of the curriculum are consistent, meaning that you don't have someone very, very young with a PhD or strange things, while 20% of them are also almost random curriculum. And so that was important to be clarified. So this is a recall of the pipeline for the screening process we are going to see today, almost in this shape in NIME. So we have, on one hand, candidates with the curriculums. On the other hand, we have a description of the job offers. Then we have a matching function that we will realize but at the end of this lecture, because it's the most complex thing to see in NIME. That is pairing the skills offered by candidates with the skills required by job offer. This matching function is producing a fitness matrix that will be the starting point of our analysis in the next few moments. The fitness matrix, what is representing? Is representing how well a certain candidate is aligned with a certain job offer. So we have the various features describing how well these two things are aligned, and at the end we have a score that is the number provided by someone of the HR from the sky, from the high. I mean, it's the ground truth that allow us to sort the candidates inside every job offer. Okay. Since this process,
Riccardo, read the chat. Read the chat. Read the chat.
Yeah, sorry. Which chat? Or the chat of this chat here. The audio is echoey. Okay, so let me try to remove to close the door.
Can you hear me better now?
Yeah.
Better. Thank you very much. I hope you grasp the main things I told you so far. So these fitness metrics, I mean, the alignment can be automatic, but the score we suppose that has been provided by humans, and therefore we want to make this process automatic, and we want to realize it through a machine learning model that, given a certain job offer and a certain candidate, is able to provide how good is this candidate for this job offer. Okay, and for a certain prediction of the machine learning model, we will have a score, the number, that can allow us to sort the candidates and have a top K list of candidates which are shortlisted and will be interviewed for a certain job, but also the contribution, meaning which are the most critical features that are responsible for creating the score of a particular candidate for a particular job offer. Okay, that's what we call the explanation. Okay. And in these two lectures, we will realize the entire pipeline. Okay, so this is an example of the fitness matrix we are going to deal with. So let's go very quickly through the features. So the first one, QID, it's an identifier of a job offer. So this is job offer 0. Okay, job offer 0, job offer 0, job offer 0. Let's say data scientist to my company, and then KID is the identifier of a candidate among those which are available. So this is Mario, the first candidate for the data scientist to my company. This one is Maria, second candidate to my position of data scientist to my company, and so on and so forth. The rest of the features up to knowledge included is representing how well the skills of the candidate are matching the skills required for the job offer. For instance, the first candidate, Mario, has not a sufficient level of knowledge for this kind of job. Language is 0.5, so perhaps Mario is speaking just Italian and is not speaking English that is required for the job. The experience is 1, so it means that Mario already had experience in some company, and so on and so forth. Okay. Finally, in the end, we have the target variable that we would like to predict through the machine learning model, score. So in this case, how good is Mario for our data scientist job in Riccardo's company is 0.484848. So we will start now from these fitness metrics. Just very quick, I will take these slides later before before the KNIME workflow. So I can start moving to KNIME. And the first thing that I'm going to do together with you is to fill this workflow that is the one with the name 0 in your folder, the one you downloaded, to remember a bit how we can use KNIME. Okay, so we are going to follow a simple analytical process on a different data set. Okay, so first thing we need to do every time is to read the data set. Okay, and I use a lot, when I use KNIME, I use a lot the search bar here on the top left. So if I need to read something, I type read, and then in this case I know that the file I want to read is a CSV file. Okay, and therefore you can drag and drop the CSV reader. Is it big enough or should I zoom? I just learned this. Okay, shortcut. So CSV reader. Now you have in every KNIME node, you have a semaphore on the bottom. When it's red, it means you cannot use the node. When it's yellow, it means it's ready to be used. And once that you play the node, the semaphore will be green. When the semaphore is green, you will have something coming out from the output ports of the node. So this is a reader node, so you don't have any input. We need to take the input from our file system. So now I'm going to double click on the node, and yes, that's what we are going to see now. Okay, here you can visualize and devisualize the list with the nodes, okay? And there are many nodes, so you can use the search bar that works very well. So now we need to read, and I'm using the CSV reader. Double click and you configure your node. Now we need to find the file. Okay, and now I should remember where I placed my example. So I have it in project, FINDHR KNIME, FINDHR course, dataset, finally. And we are going to see this example with the Titanic dataset. So your folder is probably on the desktop, so shorter path, okay? And as soon as you add the file here, you will have displayed on the bottom the visualization of the file of the first 10,000 rows, because if you have very big files, not all of them will be visualized. And from here you have a preview of the data set you are going to read. There are some settings you can play with. So by default, the column delimiter, so the symbol separating one field from the other is the comma, and that's the most important thing for now. And that's it. Basically, we can click on OK. And now you can see the semaphore is yellow. It means we can run the node. So when with adding the workflow, okay, workflow should be not, once you have downloaded from the Moodle the folder with the workflows, from the home space of KNIME, you click on import workflow. Then now I'm running this one here, practice workflow. You click on open, and after that you will have here displayed the workflow. You can click on that and you will have the workflow open. Okay. Once you have a workflow on the screen, you can select it, and if the semaphore is yellow, you can execute it. Okay. And if the node is selected, you can see the blue rectangle around. You can have access directly to the output on the bottom of the interface. Okay, so here we have the Titanic data set, which are characteristic describing passengers of the Titanic. So we have a passenger ID, the class, sex, age, if they have siblings or children, or the fare they paid, the embarkment port, cabin letter, etc., etc., etc. And in the end, if they survived or not. Now, let's see some example of nodes. Okay, for instance, here the exercise is asking us to rename the columns P-arch and P-class. Let's see how we want them to be renamed. Okay, expanded nodes. Okay, so we take, I type column here, and I look for column renamed. I drag and drop the node here, and now we are going to connect the nodes. So this is one of the most basic operation in KNIME. So you click with the mouse on the black arrow of the CSV reader, and you drag and drop. You will see that an arrow is coming out. and you connect it with the next node. That's quite intuitive, and this arrow is depicting the flows of the data. So the data is coming out from the first node and is entering to the second node. Okay, now you see the node is already ready to be played, but we didn't specify anything. So if you don't specify anything, nothing will happen. So we double click and we enter into the configuration. And now we want to rename some of the columns. For instance, instead of having sex, we can have gender to be more fair. Okay. Then, for instance, we can add a new column that should be modified. And for instance, we can change, I don't know, P class. We can call it class without this P. We don't know the meaning of having P. And you can modify as many columns as you want. You have the example on the top. I think it's quite clear. So now I decided to change only 2 columns to be faster. Now I can execute the node here, again, clicking on the top left, the execute node. Now it's green, we have the output, and we can see that now we have gender, and now we have what is class. Okay, while in the previous one there was P class and sex. Now another example of node that we are going to use a lot in the FINDHR workflows is this one to modify values, and the node is called rule engine. Actually, this time having modification of values is not really helping you to find the right node. So, I mean, to be good in using KNIME, you need to use it sometimes to know which are the features, the things you can exploit. Okay, so now we have the rule engine, and here we want to replace male and female to have them in capital letters, and 1, 2, 3 in the ticket class column with first, second, and third. Actually, this is what I've called it class in my version. Okay, so double click. Now this is much more complex interface. I hope it's good enough, because I tried to increase the font size of KNIME, but I had to reinstall it because I created a complete confusion. So it's quite hard to zoom inside the panels. Let's see what was male and female should be renamed. So here we have all the columns which are available. So we take gender, double click, it will appear here on this box. So if we say gender matches male, then arrow, it means arrow. Here you have some examples. We want it to be replaced by male with a capital M. Okay, and let's do another rule, the second one. So again, gender matches female, we replace it with female. Then we can also change class. Class, in this case, it's a number, because you see this letter here is referring to the fact that it's an integer. Remember, Daniela explained to you that every column has a different type. So S stands for string, D stands for double, I stands for integer. Okay, these are the 3 main types you are going to play with. So we can say simply, if class is equal to 1, arrow, we want it to replace with the string actually this was not, yes, this is the rule engine with the string first. Just a question to Daniela if she's listening.
Yeah.
In this case, the node is,
No, you have to use many nodes. One for one. Yeah.
This is what came just to my mind. Okay.
Exactly.
So
Exactly.
it cannot be done as I'm doing right now.
Exactly. It was tricky.
But
Yeah.
we need to do node by node. So now let me finish to write this thing all here. Okay. 2 and 3. Second and third class. Then look what I'm doing. I'm copying this here on just to avoid to rewrite all these things. I will do just for one feature, for gender. Okay, I remove all of them and I leave only gender. So the only rule I'm going to apply is if gender matches male with a small m, replace it with male with a capital M, and I'm going to use it on the gender.
Riccardo, you have to use it like so you can do it twice. So gender matches male, not gender matches male. So female, exactly. So the most important thing is to use the same column, the same nodes for the same column. Exactly.
So I can put both of them here, right?
Exactly. Not gender matches or the same. Exactly. Perfect. Okay.
Female. Thank you, Daniela, because I didn't use this node in a while, so I was not remembering clearly. So both outputs should refer to the same node, okay? So now if I apply this and I play, okay, we can see in column gender, we have male with a capital M and female with a capital F. While in the previous column, in the previous output, we have male and female with small letters. Now, let's do very, very fast also the same thing for the class, okay? For the class, feature. Class. You might have an error because they have different types, but let's see if it's working. And indeed it's working. So now we have class that is third, first, third, second, etc., etc. Another nice node is the missing value node to remove missing values. And for this thing, we have a dedicated node. You type miss or missing, and you get it. Okay. And so we can decide what to do if we have missing values with for integers, for strings, and for doubles. You can do nothing, but in this case, the node is useless. So we decide that if we have a missing integer, we replace it with the most frequent value. If we have a missing string, we replace it with a fixed value. We can place it not available. While if it's a continuous number with missing values, we can replace it with the median one, for instance. And after that, and in this data set, there are missing values. Now, I don't know. Let me see, maybe from statistics, we can see the number of missing values. No, we cannot. Okay, close to the end. Once you have done your process, so we will do a prediction of the rank for job offers, you can decide to do something with this output. Typically in Ink9 you do two things. Either you save your modified dataset into a file to avoid to repeat these things next time, or you visualize the result with some visualization with a plot, something. So let's see how to do these two things. First, we want to write the modified dataset, and so we insert a CSV writer. Again, I connect the output to this node, double click, browse, projects, no, sorry, wrong project, find HR, find HR, find HR course, dataset, let's call it Titanic 2.csv, okay, and now I want to show you the magic. I'm inside the folder. You see I have Titanic, that is the one I'm using now, and the other datasets we are going to use in the next workflows. I click OK, then I click Execute, and now I have in my folder also Titanic 2. Okay, and this is the Titanic 2 dataset. Just to show you the difference with the original one. This is the original one with the passenger ID, P class, sex, with the small male, 3, etc. While Titanic 2 has third, male with capital letters. So all the changes we did have been applied and stored locally into our file system. Finally, let's see a bar chart, for instance. Okay, bar chart to visualize what? The distribution of embarkment, okay. You see, once you exit from a node, this data can be connected to many nodes. So it's not necessarily one-to-one, but it can be one-to-many, okay? From one node, you can be connected to many. So let's see what we want to visualize. For instance, the gender, okay, in my version, and I'm going to click OK, execute, and then we double click. No, I did something wrong. I need to exclude all these columns. If I'm not. No. How was the setting? Category dimension, and that's it. Bar chart, sorry. Gender, aggregation, occurrence count. Okay, that was not specified. Okay, so we can see in this case, we want to see how many male and how many females there were on the Titanic. We specify category dimension here. Aggregation method, occurrence count, so it means you count how many, and that's it. Then you can insert a title, you can insert a category access label, for instance, counts. Category, it's on the bottom, so it's gender, probably. On the y-axis is counts, okay, and you see the plot is decorated. You can put it into horizontally, vertically, you can play a bit with this thing. And in the end, you can also generate an image that you can save somewhere. It will end up in the default folder. Now I don't know where this ends up, I guess, here somewhere. Okay, so that's it. So I'm perfectly in time. So I will take some questions about usage of NIME from those that are able to use it. Not from those having problems. For them, we have Daniela that is marvelously helping. No? Should stop?
Yeah.
Don't worry.
So Daniela, can I move on the lecture?
Yeah. I wasn't checking because there is a lot of noise here.
Okay, so now I will go back to the slides to recall to you some of the concepts you saw on the previous lectures, and then we will see how these methodologies can be realized through NIME, thanks to the notes implemented by Daniela that you found in the bundles. Okay. So the ranking algorithm that we are going to use is LambdaMart. So LambdaMart is a machine learning algorithm that is built on top of the fitness function or the fitness matrix with respect to the score, and its job basically is to provide the best possible ordering. Okay. The main parameters here summarized are the number of estimators, because LambdaMart it's an ensemble method. So it is like if a group of people are making decision together, and then the final outcome is the average of their opinion, just to summarize from a very high level. And the learning rate, that is a parameter to take control of how much every opinion should modify, let's say, the final prediction. Okay. How do we measure the performance of a machine learning method that addresses a ranking problem? The most widely used measure is the normalized discounted cumulative gain. That is a measure of ranking quality considering a top K number of candidates. Okay. The assumption that are done by the usage of this measure is that the most relevant candidates should be placed close to the top in the ordering provided by the machine learning model, rather than those which are worse and are placed to the bottom. So to say it in a very simplified way, if the machine learning model places the best candidate or the second best candidate at the bottom of the rank, last position, penultimate position, it's a very bad mistake. On the other hand, if the penultimate candidate is placed in the last position or vice versa, is a negligible mistake. So we can weight errors in a different ways. And this is done by this discounted cumulative gain formula, that is the sum of the relevance of the ith ranked candidate from I to K, where K is the short list length that we want to consider, and this impact of the closer to the top, the more important is the fact that the position is correct, is given by the fact that to the denominator we have a logarithm such that the closer a number is to the top, the bigger is the denominator, and therefore the position must be correct. Otherwise, we have a very impactful decrease in the performance. Then this discounted cumulative gain ranges from 0 to infinite, and there is a way to normalize it. We are not going to explain it in these slides. For that, we have the normalized discounted cumulative gain that ranges between 0 to 1. So for us, it's easy in the end to read that if a machine learning model has a normalized discounted cumulative gain close to 1, it means it's a very good model that is replicating the behavior of the training data, while if the normalized discounted cumulative gain is close to 0, it means that the performance are not good. Please remember that this way of evaluation is parametric with respect to k. So if you place k equals to 1, it means that you are only checking if the best candidate in the reality is the best candidate provided by the machine learning model. Otherwise, the more you increase k, the longer is the list of candidates you are going to consider. Okay? So from a certain perspective, the larger is k, the easier will be probably to have a correct list if you want. We are going to see this one later, because for now we will only stick on the workflow without any fairness assumption. So I can spoiler to you that the first workflow we are going to depict now is going to be an unfair one. Okay. So this workflow is FINDHR 2. Okay, ranking with LambdaMart. This is an overview of the workflow. Okay, and now I'm going to zoom it and explain it to you. Starting from the beginning. So we start by reading two things. Okay, we read the fitness matrix. Okay, that is the file fitness matrix 1. Okay, that is placed on your desktop under the folder dataset. And the CSV, the second CSV reader is reading the score 1. This one actually is the score 1 fair. Probably I wanted to read, doesn't exist, not fair. Score 1 unfair. Want to play with this. Okay. Okay. You can decide everyone you want to read. Then you will have time to play with this workflow. Now, my job is to explain it to you. So right now in our workflow, we have two data sets. The first one is the fitness matrix, okay, without score. The second one is the a table with just 3 columns telling to us job ID, candidate ID, and the score for this job for this candidate for this job, sorry. So now we need to join these two data sources, and to do that we use this node, the joiner, that you see takes as input, it has 2 input ports, so we connect both of them, and in the joiner we need to make a join, particularly from a database perspective, this is called an inner join, and with respect to how we designed our data sets, it's super easy, because the features we need to specify on the top table, the one coming from the top, and the bottom table to be joined, they have exactly the same name. So this schema here is telling us that we need to join the candidate ID from one table with the same candidate ID from the second table, and job ID from one table and job ID from the other table. Okay? Okay. Here you can see the result, and what we obtain basically is exactly the same data that we have from the fitness matrix, but you see here we have 11 columns, but now after the joiner we have 12 columns because QID and KID are exactly the same, okay? But now we also have the score column. So with this operation, we obtained exactly what I shown you earlier in the slides, that is this matrix here. So in this workflow, we had, I cannot probably, yes. In this workflow, we had basically these, oops, sorry. These coming from one table. These coming from another table. This one plus these two, actually. And we put them together to obtain this result. That was the operation we performed. Now, once we have this fitness matrix, a requirement that we have for from our ranking algorithm is to ensure the dataset is sorted by job ID and candidate ID. Okay, and to do that we use the sorter node that takes as input a dataset and sort it in decreasing order according to the parameters that we want to sort. So in this case, it is specified sort by job ID ascending, meaning in increasing order, and curriculum ID again in ascending order. Now, to be sincere, with respect to how it is formatted, our fitness matrix, this was not necessary because it was already sorted. But with this node, we have the guarantee that this constraint is respected. Okay, so far so good. Now we have our sorted dataset with job ID, candidate ID, the features describing how well the candidate is aligned for a certain job, and the score that our machine learning model should learn. So now it's time to prepare the machine learning setting. And in need to evaluate the performance of our model, we need to split the data into two partitions, the training set and the test set. And to do that, we use the row splitter node. Okay? All these nodes I'm mentioning can be found as earlier from the left bar. Row splitter node takes as input a data set, and the setting should be specified in a certain way. In this case, we test the column job ID, okay, knowing that in our case, so if you click here, we have some statistics. So for QID, we have 160 unique values, meaning that in our dataset there are 160 job offers. Okay, for every job offers, there might be different candidates applying. To split the data, we decide the following logic. We test the column job ID, and we keep on the upper part that is coming out from the node those having a job ID higher or equal than 159. This means that we are using 159 jobs that we have in our dataset to build the machine learning model, and the remaining one to test its performance. Okay, I remember to you that this doesn't mean that we have 160 rows in the training set, because for every job we have multiple candidates applying for that job. Okay, so we can see here the output of the row splitter. Actually, I look at two. Sorry, I said something wrong. That we have in total 200 jobs, so we keep 160 for training and 40 for the test. And indeed, we can see this from the statistics. From the top node, we have 160 job filtered. It means the top part going out, while filtered out, we have 40 jobs. So now, with the biggest part, we build the machine learning model. To build a machine learning model in time, we actually need two nodes. One is the learner, that is the one responsible for training. The second one is the predictor, that is the one responsible to make the prediction. So in the setting of LambdaMart, it is important to specify the target variable, that is a score, the number we need to predict, the query ID, that is the feature identifying, in our case, the jobs, and the features that should be excluded because these are not the predictive ones, which are QID, KID, and score, because this one is the ID of the jobs, this is the ID of the candidates, and this is the ID of, this is the target variable we need to predict. Okay? Later you can play with these two parameters if you want, the number of estimators and learning rate that I mentioned earlier. Once you have trained the model, so the semaphore is green, you can connect through this rectangle box the LambdaMart predictor, okay? That is the one responsible of making actually the prediction. So through the box is passing the model, through the arrow is passing the data. That's the different meaning of this symbol. So now we pass to the predictor, not the training set, not anymore the training set, but the test set, so the portion of data that was not observed by the learner. As output from the LambdaMart predictor, we have two outputs. The first one on the top is the normalized discounted cumulative gain score for every job. So we can see how good is the LambdaMart predictor to provide the correct ranking for every one of these 40 jobs. Okay. And what I did using a node similar to the one we used before is to show the result through an histogram. I remember to you that this number, the higher it is, the better it is. So connecting this output to the histogram, we have access to this data. And so we can see that our model is not so bad, because the distribution of this evaluation is skewed toward left, toward one, meaning that the model is performing well. Actually, for some jobs is performing very well, so it's higher than 90, higher than 80. Then for some others is not very, very good. In particular for this job here, the performance is probably not acceptable. So on the top part, we observed the performance of the model. Now in the bottom part, we are going to see if this model was fair or not through the measure of statistical parity. I'm going to explain you in a second. The statistical or demographic parity at top K measure is a measure of group fairness. So also in this case, you need K, this parameter, to consider how big is the group you want to model. How is calculated? Let's see it with this example. So we will have some candidates in the top 4 in this case, and some other candidates which are outside the top 4. In this example, we have 4 male in the top 4 and, sorry, 2 male in the top 4 and 2 not male in the top 4. So in total, we have 4 candidates, obviously, in the top 4. So just looking to the in top part, it seems that the selection was fair. However, if we look to those that have been excluded, we can see that outside the top 4, there are 8 not male, and there are only 3 male. Okay, here you can see the total of not male among the all candidates and the total of male. So among 15 total candidates, we had 5 males and 10 not males, and among these 5, 2 have been selected for the interview, but only 2 not male have been selected for the interview. Exactly these proportions I've mentioned, so the proportion of not male in the top 4 over all the not male applicants, and the proportion of male in the top 4 over all the male applicants, are the 2 proportions that are used to calculate the statistical disparity matrix. So if we do the difference between P0 and P1, so the difference between these 2 proportions, we get 40 minus 20, that in this case is equal to 20%. So we have a disparity in treatment between these 2 groups, male and not male, for the selection for this specific job of 20%. Okay? Obviously, the desiderata is to get this number very close to 0. So now let's see how we can calculate this in NIME, starting from the bottom output of lambda mart. Okay, the bottom output is providing to us what's entering into the lambda mart predictor, and is adding this last column ranking. So for every job, we have the position that have been provided to a certain candidate for a certain job. So at first, we use a row filter to select only the top K. Now, this is a parameter you can use to play in your exercise. By default is 10. So you can see how is changing the statistical parity, changing this parameter of top K. Okay? So we only keep the top 10 of the selected candidates. And for them, with the value counter node, we decide to count with respect to gender, to the variable gender. So the output of this node, it's this one here. So we have only 4 with class belonging to type 1, that is not male, and almost 400, 396, belonging to the male group. Okay? The same thing can be done starting directly from the training set. You see this arrow I'm highlighting now. So this is the same training set, the test set, that I pass to the value counter, and I do exactly the same, obtaining the total number of male and not male among those tested by the method. Then, using again the joiner, as before, we join with respect to row ID. The row ID in this case is identifying male or not male. And
Riccardo, sorry, there is a typo here. I corrected the workflow here. There is not merge the fitness metrics, but merge the selected top K and merge the applicants. Yeah, exactly. Sorry.
Okay, thank you, Daniela.
Yeah, the participant should have the correct one.
Yeah. Just to be aligned.
Yeah, exactly.
So here we merge the selected top K, and if you can see here, we have basically realized the same table I've just shown to you here. So these 4 numbers, okay? So actually, not these 4 numbers. We have, yes, we have these 2 numbers and the total numbers. Because these are the numbers that we need to calculate the proportions. Indeed, after a renaming, where we name the first column selected top K and total number of applicants, through a math formula that is simply selected top K divided by the total number of applicants, this kind of node has an interface very, very similar to the rule engine I shown you before. Okay, we created a new column proportion. And so we have this new column proportion. We have these numbers. Okay, and finally we need to use this row ID node, this ugly node. I mean, it's just something technical, but we need it to extract this information here outside, because if we look here, you see row ID has values 0 and 1. That means male and not male. In order to use these values, we need to extract them, and to do that, we use the row ID node with the configuration, create a new column with the row ID values and providing a new column named gender. So now that we have everything we need, we can, on one hand, visualize a very useful bar chart that is showing to us, you can see the disproportion in the treatment for this test set, considering this sensitive attribute gender. On one hand is 0.26, almost 27. On the other hand is 0.001. So we have a high disparity. To calculate exactly the disparity value, that in the slides is a very simple subtraction, we need all these nodes. So some things which are very complex in NIME are realized with a node, like a very complex machine learning rank on many curriculums and for many candidates with a single node, actually a couple of nodes. While to realize a difference, in this case, we need to process a bit the data to clarify the entire process. So first of all, we remove these 2 columns, which are the totals. We don't need them anymore. We keep only proportion and gender. Column filter is removing the columns. Then lagged column, I don't remember what it's doing.
No, because
it's plotting the table, so it's flattening the representation. Again, we remove the other 2 columns, and we needed to do that after, because otherwise we would have lost the reference to the 2 different proportions. We rename the proportions into proportion for not male and proportion for male. This is the same node we used in the initial tutorial. And finally, we can do the difference and observe that the statistical disparity is 0.267. Okay, and this concludes the tutorial on the ranking. Now, I stole to you the short break, so I apologize for that, but I wanted to keep everything auto-contained. So I will move immediately to the split into the breakout rooms. Otherwise, there is the risk to be late, and we will have the entire break after the FINDHR ranking workflow. What do you think, Daniela?
Yes, I suppose they are still working. They are finishing this workflow. Anna is explaining lambda mark.
Late, I'm first.
Yeah, exactly. Anna is explaining lambda mark. Yeah.
okay? But
Okay.
still time to explain what we would like you to do. So, I mean,
Exactly.
it's difficult that you comprehend this entire complex workflow at once after my explanation. So, the best thing to do is that you start to play with this workflow. So, we don't need to rebuild it from scratch. You have it, okay? Now, I'm going to split our group into 5, or Daniel, are you going to participate into a breakout room? See, okay, so six
because
breakout room, 6 groups. At first there will be at random, then I will place a tutor and myself in each one of the group. We recommend you that one of you, not one of us, is going to share the screen and start to play with the data set. So you can try to use different data sets which are available in the folder. Course dataset. So you have this version 1 and 2, okay? Job offer. Actually, you need to use fitness matrix 1 or 2 and score 1 fair, score 1 unfair, score 2 fair, score 2 unfair. So you can play with them. Obviously, you should be coherent, so either you use one version or 2 version, okay? Don't mix 1 with 2, otherwise indexes are not matching and nothing is going to work. So you can observe how are the performance of the model. You can try to vary the parameter of the lambda mark to see if you can get better performance, for instance, increasing the number of estimators or reducing the learning rate. Okay, obviously it will take more to train the model, but the dataset is not huge, so you should have a result fast enough. After that, you can play with the top K parameter to see how the results are varying, and you can check also the statistical parity. So if you have indeed a more fair or a less fair model, and that's for now. Okay, that's it for now. Starting from the beginning. So we read 2 files. Okay, we are reading the fitness matrix 1. Okay, and we are reading the score 1 unfair. We join them, okay, with respect to row ID in this case because the cardinality is exactly the same, but the important thing is to merge them with respect to job ID and candidate ID, okay? And what we obtain is the fitness matrix plus the score. The score, it is ideally the one provided by a bunch of recruiters for a certain job for a certain candidate. And is the one that allow us to provide a ranking. After that, we ensure that the dataset is sorted by job ID, named QID in our NIME workflow, and we split the dataset again into train and test. Want to underline something. In traditional machine learning, when we do training and test split, this split is done completely at random. This is something we can't do in our setting because we must guarantee to have all the candidates for a certain job in the training set and all the candidates for a certain job in the test set. Or I mean, at least it's advisable to do like that. It is better to not split this information to avoid what is called typically data leakage, and therefore the fact that we might on one hand have a false set evaluation because the same job offer that is observed by the model at training time is going to be evaluated at test time. Second thing, because the model might have more difficulties in learning if the not complete ranking is provided. That's why here in the row it is used the row splitter that is dividing but with respect to an index, in this case the index that is referring to the job ID key. In this case, I remember to you, we are keeping 160 job for training and 40 job for testing. Okay, so now in the previous, I swap very quickly to the previous workflow. Okay, in the previous workflow, after the training and test split, we had directly the top part connected to the lambda mart learner. Now it's not anymore like that, because we have the top part here connected to the LFR, standing for learning fair representation. This is a specific technique, state of the art, to change the data set, change the representation of the records in the fitness metrics to avoid a certain bias. So the purpose of this algorithm here is to learn a new data representation that is maintaining all the records of the original one, but excluding a sensitive attribute. In this example, as a sensitive attribute, we used gender. So representing the same data, but without gender, compensating for, in the representation, for the fact that certain records should not be discriminated for the fact of being not male in our precise example. Once this model is learned, as earlier, through the box, is passed to, this time we don't have a predictor, but we have a transformer. So this guy that is understanding how the data should be changed and is actually changing the data. So you can see that, again, the training set is passing from the top part through this arrow I'm following right now up to the transformer. And we can immediately see the output of the transformer. The transformer is adding new columns in this particular implementation, is adding new columns because we have, again, all the input columns that we had from job ID to score included. And I show you here, training set has from QID to score. Then we also have new columns, which are education underscore fair. Now the entire name is not displayed. Age underscore fair, contract underscore fair, which are alternative representations of the previous feature. Let's understand it better. You see, for first candidate, first job, education is 1, age is 1, gender is 0, contract is 0. If we go to check the new representation, education now is not 1 anymore, but is 0.519. Age is not 1 anymore, but is 0.449. Gender is not used anymore, okay? Because we don't want that our predictive model is using gender to provide the final ranking. So instead of having someone that has the perfect right education for a certain job offer, we will have someone that has an education of 0.519 for a certain job offer. We will have someone that has a certain age of 0.449 for a certain job offer, and so on and so forth. So on one hand, we might say that this new representation is slightly less understandable because we have entire values that might be turned into continuous values, but it is for a greater good, I have to say, that is to make this data less biased with respect to gender, with respect to score. So let's check a second which are the settings of this data transformation module, learning fair representation learner. We need to specify the gender column, the sensitive column. We need to specify the score column, that is the column that we should take into account to make the representation fair independently from the gender, and the columns that we want to include in the new representation. Obviously, all those we had at the beginning, but minus job ID, curriculum ID, gender, and score. There are some parameters. I take them from the slide to speed up it. I also had the slide. Okay. We have K to be used in the top K notion, this one here, okay. That is called in the algorithm number of prototypes. I mean, a sort of representative records you should refer to create the ranking, just to summarize at a very high level. This AZ component that by default is 0.5, that is the weight of the fair component in the loss optimized by this algorithm to learn the new representation. And this threshold here, pos th, I guess is this one, okay. Here you can find with this question mark, you can find all the descriptions. That restricts to candidates with score larger than this value to be not considered. So by default is 0 to consider everyone. Okay. So this is in summary the methodology. It's the same methodology that you should have seen also during the course. So now we pass the model to two LFR transformers. One takes as input the training set, the second one takes as input the test set, and after that everything remains like before. So we pass upper part to the lambda mart learner. Previous of this point we have a pre-processing step in which we discard all the not fair features, so we keep only education fair and we remove education, we keep only age fair and we remove age, and so on and so forth for all the columns. The same happens for the training set and test set. So the training set goes towards the lambda mart learner. We have the same upper parameters as before. You can play with again in the exercise. Then we have the test set that is passed to the lambda mart predictor, and here we have the model that is flowing to this port, and after that we have again the histogram and the calculus of the disparity. Let's see how are the performance. So we can see the performance didn't change too much from before. So from 0.89, actually they are even better. So I want to stress this fact. I mean, the machine learning model has been not corrected. The algorithm is exactly the same. It is the data representation that have been corrected to avoid a biased behavior against not male. Okay? These might impact also the performance. You don't know how. Might be towards a better result, might be towards a worse result. In this case, we got something better. And let's see the statistical disparity. The flow, it is exactly identical to before. So the bar chart, it is like this. So still we have some disparity, but I mean, this time the advantageous one are the not male. So we inverted the fact. I'm going to screenshot this to show you both plots at one. Now I'm going to open the previous bar chart. Okay, this one was the previous one. So a proportion of 0.26 against 0.001, while right now we have this box plot here. So you can see the difference. On the right, we have the one using the data transformation procedure to avoid biased behavior. So you see that indeed it was quite successful, because I mean the percentages are much smaller, indicating already something better, and we inverted the trend. Okay, so the algorithm, let's say it's slightly biased towards not male. And we can also check the statistical disparity. So earlier it was, it was 0.267, and now it is minus 0.045. So we decreased the statistical disparity by a factor of 5. Okay, quite impressive. So with this alternative data representation, we obtained a much more reliable and trustworthy automatic procedure for selecting candidates before interviews. So, okay. So at this time in my schedule, I have a wonderful coffee break. So I invite everyone to take at least 3 coffee. And we are starting back in 30 minutes at 20 to 7. We will restart with a session of practice. So I will create again the breakout rooms. I will put again people with issues with Daniela, while the others are invited again to play with these hyperparameters, switch between version 1 and version 2, and see if through the this methodology we have discussed now, or changing its parameters, you are able to reduce the bias in the final prediction of the algorithm. Play with the second workflow that I repeat to you, it's identical to the first one. I explained it more slowly, but with addition of this learning fair representation module. So you are invited to play with both parameters, with the parameters of both this module of pre-processing to make the dataset fair, and with the lambda mart parameters to see how the performance are changing, how the statistical disparity is changing, how things are changing var in k, the number of candidates selected, etc., etc. You can play again in data sets with group 1 or group 2. I remember to you that if you change something at the beginning, okay, if you change a data set, for instance, and therefore everything is resetted, you can also reset everything using this reset all node. You can either click execute all when you are not selecting a specific node. So if you click on the white screen, then you have access to execute all. Or if you reach a terminal node or any node, and if you run it, you can run the node either from here, small play symbol when you go mouse over, or on the top left here, execute. All the previous nodes are going to be executed and you have access to the result. Okay.